Right.
And our next speaker up is Fatemeh from Monash University.
Sweet. Thank you.
Thanks very much, Yinglu.
Okay, I just share my screen. Can you hear me clearly?
Yes, I can hear you well. Thanks. Go ahead and share your screen.
Okay. So can you see the correct screen?
Excellent. That's right.
Okay. Hello, everyone. I'm Fatemeh. I'm doing my PhD at Monash. My research is about the link between craton margin structures and base metal mineral systems in North Australian Craton. So I'm just going to walk you through some background literature, what I do in my research, and what we have done so far, and what we are doing at the moment to answer the research questions. So basically,
Fatemeh, sorry,
yeah?
Can I just interrupt? Have you got some sort of window open or like a window in front of your? There is a block in front of your screen. That usually means there's like a dialog box or something open.
Okay. Yeah, I think I got what you said. Let me just fix that.
Sorry to interrupt. Otherwise,
no, I just moved, I think, the audience window to the other side to not interrupt myself. Sorry, that was that's the reason. Yeah, no, thank you for telling me. I just try again. Sorry. Okay.
Still there.
I know, I just move it to here. Okay, is that
perfect?
Just I need to fix it. I don't know. Okay, so
that's good now.
Okay, let's keep going. Sorry for that. I just go to the slide I was showing. Yeah. So this map shows the location of Archean and Proterozoic cratons around the world. And also what we have, the background map is the crustal thickness. And the dot shows different base metal mineral systems around the world. And so as you can see with the red arrows, the location of base metal mineral system globally shows a special correlation with craton margins. But this spatial correlation has been examined through different studies, but what is missing is why some segments doesn't show the same correlation that, like I show some point sublocation with the blue arrow. So there are many research around this topic. In one of the most recent papers by Hogarth in 2020, they identify a special correlation between base metal mineral sediment hosted base metal mineral system and craton margin, and they showed that 85% of these mineral system are within a 200-kilometer distance from craton margin. And this result also was consistent with another study that has been done with by David Groves in 2020, that they showed that most of the mineral deposit are within like 100 kilometers of margin of Archean cratons. So all the research basically they did a good job in narrowing down their search space for different type of mineral system. But what is this significant thing about craton margin that impact the mineral system endowment? So, and this correlation is far more complicated than just narrowing down the search space by a buffer distance. For example, if you look at, I just choose it. If you look at North Australian Craton that I am showing here, on east side of it, we have like high mineralization, and the other side, we don't see the same like relationship like what we see in a global scale. So therefore, we need more detailed information to tell us what is the link and what is missing here. So therefore, what we do not know is that how mineral system link to the craton margins, and basically whatever we know so far about mineral system is more about like how they form rather than why they form and why on some localities we have mineral system and on other localities we don't have. So therefore there is this gap in our understanding, and we need to work on how the craton margin geometry controls mineral system, and if it controls mineral system or not. So in my research, what we do, we are working on this hypothesis that geometry of craton margin controls the base metal mineral system in the upper crust. And for testing this hypothesis, we have some research question. Like first we work on like what is the geometry, how does it look like, how we can image it, and then what is the process, and how basically what is the link between this geometry and upper crustal structure, and what links them together, and whether there's a kind of like global framework that we can apply to other cratons around the world. In my research, we classified the craton margin geometry in 3 categories: steep dipping, inward dipping, and outward dipping. And like we use that as a reference book throughout the presentation. So for this study, we needed to choose a craton to work on. So we investigated the Australian Cratons. We know that 66% of Australia is made of Archean to Proterozoic cratons, and their margins, the location of high mineralization, and also like high deformation, and also fluid flow at all crustal level. And what we know is that in Paleoproterozoic to early late Paleoproterozoic to early Mesoproterozoic, it was like a time period that most of like this world-class mineral system formed in Australia. And for my study, we chose North Australian Craton, or I refer to it as NAC throughout the presentation. And this is a very significant craton, is an amalgamation of fragments of like Archean and Proterozoic age fragments that they stitched together during the Barramundi orogeny. North Australian Craton, as I said, has some kind of different mineralization on different sites, like they are contracting margins, and we have like an excellent data set available, like geophysical data set and also seismic data set that we can use. So that's why we are working on this craton. And also the 2 main margin that I'm focusing on are the eastern margin Mount Isa and southern margin Arunta. Okay. So this slide shows a time-space table for NAC evolution in Proterozoic. On the east, we have Mount Isa is highly mineralized, and we have like high endowment of mineral system. It has experienced multiple cycles of extension and compression in basin development and inversion, and it's been divided to 3 main like major fold belts, like eastern and western fold belt, and also in the center we have Chalcedon-Leichhardt belt. And geophysical interpretation suggests that Mount Isa is has collided with Numil block, and the suture zone between these two is Gijia suture zone on the east side. And the other margin that we said is Arunta in the south. Arunta is less mineralized than Mount Isa. And also we have 3 major sites, like northern part of Arunta, central part, and southern part. And there are 2 major sutures identified in the area. And we have Varumpi, where Varumpi collided with the NAC, like is a much younger train. And also we have Villora in this side that is where Aileron and Devonport collided with each other. And one of apart from mineralization, the other significant difference between these 2 margins is like their tectonic evolution and the number of like major superbasin that we see in the area. And like these superbasin are basically the host for all those base metal mineral systems that we are talking about. So for imaging the geometry of craton margin, we have been using multiple type of data set like gravity, mag, seismic data. We use like the most recent like model we have for MOHO, and also the seismic tomography data, it helps us to be able to identify geometry in different levels. But when I'm talking about geometry, basically is the major suture and major crustal and lithospheric scale structures that we see at the margin. So the first margin that we worked on is Mount Isa. And as you can see here, these black line are the major structures in Mount Isa, and the red line are the seismic lines that I worked on. We know that there are lots of, like we have some interpretation of this seismic line, but we reinterpret everything like in sake of like consistency, and also to see what I see in them different from other people. So basically, we did like 6 lines in Mount Isa, and this interpretation identified 3 major suture or major crustal scale structure: Giza suture zone, Pilgrim Fault, and Western Edge Fault. And so one of the first thing that I want to show is that we identify the Giza suture zone, like is a well-known suture as a west dipping structure. And as I said, it's where Numil block collided with Mount Isa. And the other structure that we identified is Pilgrim Fault. Pilgrim Fault is mostly known as an upper crustal scale structure, but based on our interpretation is a crustal boundary between east side and central side of Mount Isa, and it also has a west dipping structure. And I don't talk much about the Western Edge Fault because it's mostly like where this margin of Mount Isa, neck, is kind of like linked to the other side of the neck. But what I'm mostly interested is this side. So as I said, like Giza suture zone is where we have Numil block collided by Mount Isa, and we see it like it shows a significant signature of sutures, like in different geophysical data. In seismic reflection, we see that on like one of the major signature is that on Numil side we have like this distinctive seismic reflection pattern, while on the Mount Isa side of it is more like a faded pattern, and we don't see that. And this indicate the collision between Numil and Mount Isa around 1.8 billion years. And we identified the Mount Isa margin as an inward dipping margin, and this suture has a dipping around 55 to 65 degrees to west. And also what we saw in Pilgrim Fault is that it showed different signature at 2 different sides, and also it has been shown to in other papers that it has different signature on both sides of it. And yeah, we also see some kind of like offset in the reflectors, and we identified as a west dipping structure with 60 to 75 degrees. And both of this structure, as I said, they show this, they are the location of the intense gradient in potential field data, and they show the known signature for sutures. And in our interpretation, we are somehow sure that Pilgrim Fault is a major crustal boundary. And also in other papers, it has been shown that it has like different isotopic signature on both sides, and it seems to be like where 2 different basement blocks collided with each other. So the other boundary that we investigated is Aronta. We work on 2 seismic lines in Aronta, and they confirm that we have 2 sutures, Villora and Vrumpi. In the north, we have Villora Ridge, and it has like an east orientation. It's dipping outwardly. So here, Aronta has been classified as an inward dipping structure. And Villora is shallow, it has shallow dipping of 40 degrees. And in also seismic interpretation and other research, it has been shown is like a kind of suture, and its age around 1.85 to 1.84 billion years. And the other suture we saw is Vrumpi, and this is where We have also like a kind of east west oriented structure, but it's dipping toward north, and it's more like a steep dipping, like 78 to 80 degrees, and it's like where we have a younger block like coming towards NAC and collided around 1.64 billion years. And it also represents the Central Australia suture. In our research, we chose Villora as the most southern edge of Mount Isa, and we classify it as outward dipping. So Mount Isa is inward dipping and Oronta is outward dipping. So you can see they have quite different geometries. So after that, we wanted to know how they link to the upper crustal structure. We mostly use for this part potential field data and seismic reflection interpretation, and also we had like the surface geology as a reference to just be correlated with each other. So so as you can see here, these are two major structure, Pilgrim Fold and Giga suture, and this structure in the upper cross, they seem to have like a comparable pattern. Giga suture can, like for example, connect to Cloncurry fault zone, and Pilgrim Fault connect to Mount Isa fault zone in a kind of listric fashion. And they have like different like deep direction, like they have different deep direction. And our observation suggests that most of the major structures develop in the hanging wall of the sutures, and the mineral system form in the hanging wall of these listric faults. So therefore, so we have this crust penetrating structure, and that they can be as like a first order control on mineral system. So they provide a pathway for fluid that just feed into this upper crust structure and help to create the mineral systems. So this link in Oronta is quite different. In Oronta, we don't see that listric fashion for upper crust structure. The structure are like, for example, in Villora Ridge that we chose as the southern edge of Mount Isa, they are parallel to the major suture. They go, most of them go all the way down to Moho. The whole fracture zone, spacing between a structure in Oronta is more than Mount Isa. And also other research that has been done in this area, like Shay explained that this area has like a kind of thick-skinned deformation in the basement and thin-skinned tectonics in the sedimentary cover. And the pattern and the link that we identify shows that we need to understand what is the process. So there is a kind of correlation between geometry and the like pattern of a structure in upper crust. But what we need to know is that how they link to each other, and rather than correlation, what is the causation? So how we can test this correlation in fact. So in this regard, we designed a series of analog modeling. So this analog modeling is like a big project. And in this project, basically, we want to see the impact of what we call it a scar or like a weakness in different like layers, like lithospheric mantle, lower crust, and how impact the propagation of a structure in the upper crust. We have 3 series of structures. The first series is just basically just look at different type of geometry in the lithospheric mantle. And in the second series is where we also, apart from like the geometry, we have different materials on each side. So on the gray, like the gray color shows the craton side is like where we have a more like stronger material. And in the third series of experiment is like where we extend the geometry to the lower crust and see what's the impact of that on upper crustal structures. So what I'm going to show you are some results from the first series of like the reference experiments. What I forgot to mention is that these experiments are in collaboration with Dr. Samso, and she's my fourth supervisor, and she's doing the first and second series of experiments in uppermost mantle, and I'm doing the experiments in lower cross. So I'm just like what we did, basically, what we are trying to do, we are trying to reproduce a rift zone and try to extend it and create a rift zone, and then do some kind of compression and invert the basin and create like a kind of origins. So I think if I can play this, that would be perfect. So as you can see here, what the video is showing is like the kind of extension we had, and it's just our reference experiment so far. And here is a 3D view of that shows like the surface and the topography. And you can see when we have an extended basin or a region, and then we compress it, it recreates some origins along the rifts. So basically, we are at the very earliest stage of these experiments. So what we are looking for basically is to see what the geometry caused in terms of like changing the pattern of like structures in the upper crust, basically, and how we can link it to what we observe in North Australian Craton. So in my experiments, as I said, I just work on low crust and upper crust. So I am going to create, like here, represent the yellow line represent the boundary or suture, is I'm going to play around with the geometry of this suture and see how it impacts the propagation of structure. And so when we need, but before that, we need to understand what is the contrast, strength contrast on each side. So we have like a craton side and a mobile belt side. So how we can represent that, we know that like craton in terms of like maybe rheology and the mobile belt side doesn't have that much difference in terms of rheology, but what we know is like, because craton is like this thick, cold, buoyant lithosphere, and it's next to like a thin, weak mobile belt. So they have quite like different strengths. So what we are first trying to understand in my experiments is like, what should be this strength contrast that represent what we see in Earth. So in my experiments, first, I just work on this ratio between the different materials and try to figure it out what is the best suitable value. And in the second series of my experiment, I'm basically looking at different geometries. So I'm going to recreate an inward-outward dipping and see how it impacts the whole structures. So the good thing about analog modeling that I should mention is that it gives us, like my apparatus will give us this chance to have like cross-section and 3D views, and we can compare that with seismic interpretation, and the map view we can compare with our interpretation from potential field data. That we hope that at the end of this experiment, we can somehow be able to explain how the structure form. And the last part of my project, which is like, I haven't done much about it, I just maybe tried a little bit to figure it out, is how the mineral system endowment or mineral endowment linked to these structures. We know that previous study talk about like this distance, but they generally talk about a buffer zone. But what we do, like so far I found, is that we need to know whether, what is the geometry, like inward or that outward. Are we in the hanging wall or the football? Because the story can be quite different on each side. And then it can give us an understanding of, okay, can we expect any mineral system to be in this area or not? So we can have more information in that terms. And when I played around with the distribution of mineral systems around the board, when you go on and work on a specific like mineral system like OSDGs, VMS, or other type of mineral system, you can see this correlation is not that high as it has been mentioned in previous studies. So it's quite simple, even like maybe we ask, okay, how you have like this huge data set, which is significant in Australia, how can you use, how can you compare it with another craton, like for example, in Canada or China? So basically, if we have like some global model of that shows us the moho and like basically that indicate the crustal and lithospheric edge, then we can somehow represent, okay, is it like generally inward dipping or outward dipping? And then we can figure it out, is it like, are we in a hanging wall or footwall? So far I just finished my second year, so I'm still in the middle of my PhD and try to figure it out these problems. But so far we found out like east side of Mount Eliza is inward dipping, south side is outward dipping, and we have different like pattern in terms of mineral system, like east side is highly mineralized and south side is low mineralized. And also the whole story around like structures pattern is different. So what we know is that we think that we can somehow explain why some regions are highly mineralized and some segments are barren. And we hope that we can investigate the causation of this relationship further with analog modeling. Thank you so much.
Excellent. Thanks very much, Fatemeh. That's a great talk, and I'm thrilled to see some modeling that extends a basin, does extension and then inverts it.
Yeah.
I've been looking around for some examples of that, because that's what I always want to see.
Sorry, I went over time as well. I was just trying, because I wanted to show you some of the things that Dr. Samso is doing at the moment. So
that's excellent. Likewise, I'll have to catch up with you and have a more detailed
we
chat.
should definitely.
Yeah. So actually, given the time, we will move along. If
That's
anybody
okay.
has any questions, please put them in the chat box, and Fatemeh can answer them online.
Yeah, I do.
and or we can talk more at the end. I'm looking
Yeah,
forward
sure,
to the final
definitely.
discussions.
Thank
Excellent.
you.